Good evening. Good evening. If I can get your attention, please. Good evening. My name is Len Shustak. I'm chairman of the board of the Computer History Center, and I want to welcome you here. My job here tonight is to say a few words and get off the stage as quickly as possible so that we can hear all these wonderful stories that I'm sure will amuse and entertain us for this evening. First, a couple of marketing questions. How many of you are here for the first time? Sprinkling. How many of you found out about this event from Craigslist? Okay, that's obviously not a very effective marketing tool for us. I hope while you're here you've seen some of the exhibits downstairs. Visible Storage, of course, which has been around for a while, and the chess exhibit, which opened last year. Also, there's the great photo exhibit by Lee Friedlander of Cray photographs, and they're terrific. They won't be here for very long, so if you haven't seen them now, go see them after the event. They're actually wonderful. The other thing that you might have enjoyed downstairs is a Cray-1 that you can actually sit on. The one in our visible storage and the others in our collection we don't allow people to do that with, but the one downstairs with carefully reupholstered cushions, courtesy of Betsy Toole, John's wife, is actually sittable on and actually has lights inside that are still working. None of the rest of the machine, of course, is working. But that's one of the fun things. We're leading up to all sorts of exhibits at the Computer History Museum, and I hope you stay tuned for them. We're working to fill this second floor with a 15,000 square foot exhibit on the history of computing. So stay tuned for that. In the meantime, we have lots of things to visit in Cyberland. The chess exhibit and visible storage are both online at computerhistory.org. Check that out. One of the more recent additions, courtesy of Papilia, is a MyCHM subpart of the website. So you can tailor the website to look at the things that you have particular interest in. So please visit the website. That's also the place where you can find out announcements of upcoming events. And obviously you're looking at that rather than looking at Craigslist, so that's wonderful. I'd like to thank the sponsors of this event, people who know a little bit about Cray and supercomputers, Cray Inc., with a direct line from Cray Research and Cray himself, and Linux Networks, networks with an X, Linux Networks. We're proud to have them supporting us today. So, after this event, by the way, we will have a cake ceremony celebrating the 30th anniversary of the Cray-1. So stay tuned for that and stay around for a piece of cake. The Cray-1 is an icon. There are wonderful objects that we design all the time. Many of them are beautiful, many of them are useful, but very few of them become icons that become a representative of the culture of our civilization. The Cray-1 is that. It's up there with the Volkswagen Beetle and the iPod as things that people recognize as important contributions to civilization. And of course, the designer, Seymour Cray, was a legend, and many of the people who are up here today knew him personally and will tell us, I'm sure, wonderful stories about that. To start us off, I'd like to introduce Tom Marazzi, who is currently with Cray Inc. Tom started out in the U.S. Navy, where he worked on one of Cray's very early computers, the CDC 1604. He went on thereafter to work at CDC, at Cray Research, and now works for Cray. He knew Seymour personally, and I'm sure will, as will the others, tell us wonderful stories. So please welcome Tom Marazzi.
Good evening. Cray Incorporated, the remaining company from Seymour's career with control data leading to Cray Research and now Cray Incorporated, is a lot smaller company than it used to be many years ago. We're 800 employees with offices headquartered in Seattle. Software development is still done in Mendota Heights, Minnesota, and manufacturing is still done in Chippewa Falls, Wisconsin. Chippewa Falls 30 years ago was 12,000 people. Today it's all the way up to 13,500. The main industries then were supercomputers, shoes, and beer. And today the main industries are supercomputers, shoes, and beer. The industry that grew from Seymour Cray's work offered many of us in this room opportunity to earn an income, raise a family, and grow an industry. And we've done things like buy these machines or sell these machines, support them, write software for them. and do the research with them that as a tool that couldn't have been done in the past. And so I would take a minute to encourage us with gray hair or no hair to mentor the next generation of people that will carry on this work, because this is an industry that will continue to grow. My main function this evening is to introduce our moderator, for this evening, who is Burton Smith. Burton is internationally known in high-performance computing, probably knows most of you. He graduated from MIT, taught at the University of Colorado, worked for the Institute of Defense Analysis, and spent 6 years at Denelcor as the primary architect of the HEP machine. In 1988, he was the founder and chairman of Tera Computers and the primary architect of the multi-threaded architecture machine. In 1991, he received the Eckert and Mauchly Award. At Cray Inc., he was the chief scientist, member of the board of directors. In 2003, he received the Seymour Cray Award from the IEEE. Burton is currently a technical fellow at Microsoft Corporation. Ladies and gentlemen, please welcome Burton Smith.
Thanks a lot, Tom, for that glowing introduction. I don't know how I got this job, except maybe I met all these guys more or less at the same time at Los Alamos years and years ago, back around 1980 or so. And they and some of the other people in the audience, like George Michael, are sort of responsible for my education in high-performance computing, such as it is. And so I figured, you know, since I sort of knew them all fairly well, they were willing to tolerate me as the introducer. There's something else I want to do, though, and I'll get to that in a minute. But over here we have Jack Worlton, who was the person responsible for acquiring the Cray-1. Stuck his neck pretty far out, I think. He may not agree, but I think it was a pretty bold and of course, a very, very good move for the laboratory. When I went down there in 80, Bo was the head of C division at Los Alamos, and Bill, on his left, you're right, was his deputy. And you know, there was a lot of interesting things to say. So these are the right people to talk about that first Cray shipment from Cray Research to Los Alamos, and why they bought the machine, and what the problems were with it, and what happened next, and a little bit about Seymour and everything else. So I think this is a great group of people to start things off. I think you understand, of course, that you all have a lot of things to say here too, Seymour stories and other things, and we expect you to speak up when the time comes. And you know, I expect if you raise your hand in the middle of somebody talking, it'll probably be to raise a correction or point of order or something, and who knows, maybe you'll get recognized. So with that, I'd like to sort of start off here and give you a little background on the Cray-1 itself, actually. I didn't know Mr. Cray very well at all. In fact, I only met him once, and we had a very interesting exchange, which you can read. I never really wanted to talk to him about computer architecture because, as I say here, it'd be sort of like talking to Mozart about composition. I mean, it's sort of like, you know, what is there to say, really? And, you know, he did his thing and I did my thing. And in fact, I think if you know how Seymour treated heterodox ideas, he would basically say, well, that sounds like a good idea. Why don't you go do that? As opposed to, oh, yeah, I'm going to do that right away. So anyway, so what can I talk to you about, not knowing Seymour that well? And I thought, instead of talking to you about Seymour, I'll talk to you about the Cray-1 a little bit. The Cray-1 was an absolutely remarkable machine, just tremendous. And it had some flaws too, but it was just an amazing thing. So I'd like to give you a little bit of appreciation. This is serial 1 at Los Alamos on the floor with sort of the classic multicolored panels going around. And you've seen these things before. The thing on the left, if I'm not mistaken, is a thing called the iOS. And it's kind of fun. The iconic shape is mentioned just before. The fact it's very small. And the I/O subsystem looks like someone has already cut you a piece of the cake. So we'll see if the cake downstairs actually resembles that shape. Knowing this museum, it might well. It shipped in lots of colors. Some of them were a lot uglier than others. I recall a perforated metal skinned one, sort of looking like the bottom of a screen door got applied to the sides of the Cray. And it was at Los Alamos, I think. And none of the panelists remember this machine, but it was terminally ugly. So you could sort of have it any way you wanted. The circuit boards seem to be tapered, but they aren't. They're square. And it's shaped like this letter C, which the 7600 was as well. It's just a block C instead of a round C, but still.
And the T.J. Watson Research Lab was that way too.
That's true. Did Seymour ever work at Watson? Gene, no, that can't be right. All right. Things you might not know. I mean, you probably know everything I'm going to tell you, but anyway, here's some things you might not know. The bench seat sometimes was a bed for tired installers. It got to be 11, 12 o'clock at night, and they just have a little nap. Bob Gore, the inventor of Gore-Tex, invented it for Seymour. The reason is that since it's mostly air, as opposed to Teflon, which has a dielectric constant of around 2.8 or something, air is pretty close to 1, so light travels a bit faster. To be exact, it travels the square root of 2.8 times faster or something in Gore-Tex. So expanded PTFE was invented for supercomputer wires, not for backpacking clothing or anything like that. The other thing you should know is that every Cray-1 shipped, and lots of other Crays shipped after that, included a case of Lineys as part of the shipment. And I don't know who drank the Lineys, but maybe some of my colleagues over here can tell you. We do. Yeah, okay. Right. The packaging of the machine was truly amazing. First of all, it's 5 tons and 150 kilowatts, and that's actually not that surprising for a mainframe class computer. But it was a very simple machine. It had a megaword of memory in it, absolute tops, which is 8 megabytes for those of you who think in bytes. The Cray-1 doesn't think in bytes. It's 64-bit words. Sorry, you just learn to love it. And we do. There were 24 chassis, sort of 12 by 2. 16 of those were reserved for this memory, for this colossal 1 megaword of memory. The circuit boards were 6-inch by 8-inch, and they were mounted 2 at a time onto modules, which had a copper sort of thing in the middle that conducted heat out to the edges. Bill may have something to say about that at some point. He's going to talk about plumbing. Anyway, this was a very clever way of getting heat out of the system without moving air around. As a result, it was a very dense package, and that's how you could get all of those 662 modules into such a small space. All the signals traveled on the surface of the board, which gave them an advantage speed-wise, because the dielectric constant seen by those transmission lines was a hybrid of air and the material of the board, and so light traveled a little faster there than it would buried in the board, and Seymour used that to advantage. The inner layers, there were 3 inner layers, and they were minus 5.2 volts, minus 2 volts in ground. And then everything off the board went via differential pairs through some very interesting white and blue twisted pair wiring that you can see downstairs if you look at the machine. So very dense packaging made possible by this conduction cooling through this copper plate to cold bars at the side of the machine. The logic was discrete logic, as we might call it today, hardly even medium scale integration. In fact, the main building block of the machine was a dual 4 or 5 input OR, built from a technology called Meckel 3, which was very, very fast, sort of a typical propagation delay of less than a nanosecond. Edge speed was typically slower than the propagation delay through the gate, so had nice slow edges relative to its relative to the delay through the logic. And a very linear technology, very nice to deal with, very power hungry, however. There were actually 3 kinds of or-nors in the system. There was Meckel 3, and as the Cray-1 manual will tell you, there was also Meckel 10K used for address fan-out in the memory system. But there was a 3rd kind that I happen to know about from my Denelcor days. I knew that Cray was actually selecting certain of the Meckel 3 or-nors to use in the clock tree. He wanted things that, that didn't vary much from chip to chip, so that any of these chips could be put anywhere in the clock tree to minimize skew getting from the root of the clock tree out to the leaves. So that was a kind of a cool deal. I have visions of people in Chippewa Falls carefully measuring these little gates. Also in here was a 1K by 1 RAM part, which was main memory. So this is a ECL static memory used as main memory of the machine. Pretty power hungry. And then a 16-bit register file for things like instruction buffers and so on. Clock rate is 80 megahertz, 12.5 nanosecond clock, which was blindingly fast in those days. Not anymore, but in the day, man, that was fast. It was hard for a lot of us to imagine how Seymour could design logic that actually ran that fast. And the answer was, well, it was very simple. What he was doing was engineered to support that, and very simple. Everything in the system was a transmission line. Every way a signal got from point A to point B was transmission lines. And what he did was he parallel terminated every output of every one of those or-nors. That is the true and complement, whether they were both used or not, didn't matter. He put a 60 ohm resistor from there to minus 2 volts to terminate the logic. And what that meant was that the current that that or-nor drew from the power system was constant. Okay? ECL technology is linear. It switches linearly. So there was just constant current being drawn from the power supply. How he used that, you'll see in a minute. So here's a picture of that dual 4 or 5 input or-nor. This is very un-Seymour-like. Seymour didn't pay any attention to these schematic symbols for things. He wrote everything in Boolean equations. And it was for other people to translate the Boolean equations into things like this. Boolean equations is a higher level way of designing logic than schematics, which we used to do. It's more akin to writing in Verilog or VHDL today. The trouble was he didn't have compilers, he didn't have synopsis, he had people that would translate his Boolean equations into logic. Here's a Cray power supply. There are 36 of these sitting underneath the benches that you're about to sit on. And they weren't regulated at all. They were just full-wave bridge rectified and filtered with a choke. He used the board capacitors for the capacitor in that LC filter. This is rather ingenious. He was able to do that because there were bus bars connecting everything up, and it was just more inductance. He had a choke in the power supply, and he had some more inductance in the bus bars, and then he hung capacitors across the bus bars. Well, that's ingenious, isn't it? I thought. Anyway, and the constant current meant he didn't have to regulate anything. On top of all of this, the system was powered by a 400 hertz 3-phase motor generator set. Now, 400 hertz 3-phase is a lot easier to filter the ripple out of than 60 hertz 1-phase. 60 hertz 1-phase generates 120 hertz ripple frequency. 400 hertz 3-phase generates a 2.4 kilohertz ripple frequency. So it's a lot easier to get the bounces out of it. You get almost pure DC just coming out before you filter anything. It's very, very nice. Here's I don't know how much of this you can see, but here's the whole functional unit and register picture of the machine. This is sort of what's inside. And it's really a very, very simple machine. There's sort of 3 main sets of registers in here. The vector registers, which occupy the prominent position at the top. The scalar registers, 8 of them. There are 8 vector registers as well. The 8 scalar registers are located in the middle, and that's sort of where normal sorts of data go. And then there are address registers. Seymour had this propensity to have different architected registers for addresses than for data. He didn't put floating points somewhere else. He mixed floating point and integers among the data, but he had address registers. And in fact, if you want to see the pinnacle of that, architectural idea, you could look earlier at the CDC 6600 or 7600, which had some very ingenious ways of taking advantage of the fact that you knew which registers had addresses in them. Anyway, it was a Seymour Cray kind of concept. There are also some. There's an instruction cache of an unusual kind. It's four-way set associative, but there's only one set. And the cache line is rather long, and that's four things in the lower left. There's I/O, which I'll neglect just like everybody else does, at the bottom center. And then there were some S and some T registers and some B registers that were used to back up the S and A registers, the address and data registers, so that you didn't have to spill all the way to memory. A whole 11 clocks away. Wow, those were the days. Instead, you could just put them in the B registers if they were addresses, or the T registers if they were data. And compiler writers use that to some extent. There were some unusual features on the Cray. Of course, there were no byte addressing or partial word addressing or whatever. There was also, that bit vector thing applies to the next three. There was some support for bit vector data type, that is, unaligned vector of irregular length integers or sequences of bits or whatever. The machine had the ability, for example, to take two registers and treat them as one long register and shift it, and then select out a piece of it, or merge bits from two different words, things like that. One of the really, really valuable features of the machine that we've lost almost completely in our business is a user-readable clock that was accurate to cycles. That was just tremendous in performance measuring, especially. And it's not that hard, folks. Let's restore that to currency. The arithmetic, the floating point arithmetic, was decidedly not IEEE compliant. Besides 48-bit significans, it had errors of a few units in the last place. And the most infamous thing was the non-commutative multiply. If you look at the multiplication implementation in the Cray-1 manual, you'll see that low-order bits are dropped in an irregular, jagged way, which caused floating point multiply to not be commutative. And you had to do integer multiply and divide. Anything bigger than an address, you had to use the floating point hardware to do that. The last two things I'd like to talk about really briefly, though, are really unusual things. One is a very important thing called chaining, which was a way to essentially allow one functional unit to take results coming out of another functional unit that was doing a vector operation. So instead of waiting for the whole vector operation to be done, you could sort of overlap the two vector operations. There's a little more detail that I think we need to get into. But I did want to say something about this, which you should not try on any Cray except a Cray-1, I believe. I don't think that once flexible chain slots were introduced, this feature went away, unfortunately. But this was a great thing on the Cray-1. And what it was the ability to do partial reductions using this chaining facility. Basically, what you did was you fed the register back to itself. So, it would say, well, I'm going to add me to myself, and, some number of clocks later, determined by the delay of the functional unit, something is coming out of the functional unit that's getting added into the thing that's already in the register. So essentially, you get this recursive addition, in this case, for a floating point add that's every 8 clocks. And as a result, you could take a 64-bit word full of floating point numbers and do one vector instruction and get back a result that had, 8 numbers instead of 64. If you just add those 8 numbers together, you're done adding all the elements of a vector. Very, very clever idea. Well, that's enough from me. I'd like to get to these guys who have the real story. But I wanted to tell you a little bit about the Cray-1. It's a masterpiece of engineering, absolute masterpiece. I don't know there's anything quite to touch it in terms of being innovative, really stretching the computing business in a way that some of its predecessors, like the TIASC and so on, were not, or the ILIAC 4 for that matter, were not able to do. There were a number of reasons why that's so. But it's really remarkable. The other thing is the Cray-1 is only part of Seymour Cray's legacy. His famous machines are listed here. There's some more that are less famous. There are examples of some of these in the museum. Anyway, it's really exciting for me to honor the guy and his most memorable achievement, I think, which is the Cray-1. So without further ado, I'd like to call on Jack Worlton to tell us something about, so how did Los Alamos come to get one of these systems, or what?
There we go. In January 1975, Seymour Cray gave a lecture at Los Alamos in which he described his new computer, the Cray-1. Seymour rarely gave lectures because he was too busy designing and building computers. But when he did give one, he was charming, witty, and with his deep technical knowledge, he was very interesting and very persuasive. At the end of his lecture, we were completely convinced that we should have one of his machines. However, he threw cold water on our plans when he said there was some prospect that the first Cray-1 would be installed at Livermore. Now, telling a Los Alamos audience that the first Cray-1 would be installed at Livermore when they were already in the process of getting 2 new vector machines was not likely to be received happily at Los Alamos. And well, Seymour knew it, and he brought it up deliberately to prod us. And it worked. I immediately went back to my office and began writing a proposal for the installation of the first Cray-1. And to make a long story short, that proposal was subsequently approved by the Division of Military Application of the Energy Department. However, there was a problem. This was an unbudgeted item in the middle of a fiscal year, so we had approval to get the Cray-1, but no money to pay for it. We began looking around for money that could be redirected for that purpose, and of course that took time. But time was something this new computer company, Cray Research, didn't have a lot of because they were just a startup company with barely enough money to pay for basic things like salaries and utilities. From their point of view, this couldn't go on longer. They'd go out of business before they could make their first delivery. So in his typically ingenious and daring fashion, Seymour offered us a proposal. He would install the first Cray-1 at Los Alamos and let us use it free for 6 months, and if by then we had found our money and wanted to keep the machine, fine, we could buy it. If not, we could return the machine to Cray Research with no questions asked. It was an outrageous proposal, but of course he knew we'd never do that. In the event the money was found, I think the government borrowed the money from some rich Texas oil man or something strange like that, and we bought the machine. Other customers quickly lined up for a Cray-1, perhaps influenced somewhat by the favorable experience at Los Alamos with the new machine, and it wasn't long before Cray Research was a profitable company, eventually selling more than 80 Cray-1s. Now, this has been just a 3-minute summary of how Los Alamos got its first Cray-1, and it doesn't explain why Los Alamos chose the Cray-1 rather than some other computer. To understand the transition from the 7600 to the Cray-1, it's necessary to revisit 2 computer projects undertaken by Control Data Corporation in the early 1970s, the 8600 and the Star 100. The 8600 was a project begun in 1970 by Seymour Cray that was intended to be a follow-on to the 7600. Like the 7600, it used discrete components, that is, individual transistors, capacitors, and resistors, each of whose wire leads had to be soldered to a circuit board. However, because the 8600 was a 4-processor design, it was much more complex than the single-processor 7600 had been, and the much larger number of solder joints, each of which had some probability of failure, invoked the curse of the tyranny of large numbers. The machine was irreparably unreliable, and Seymour abandoned the project in 1971. In effect, Seymour had carried discrete component technology a generation too far. Now, the self-confidence, the boldness, and the ingenuity of great leaders and inventors sometimes lead them to skirt the edges of success and failure. And this can lead even the greatest to have a few failures in their careers, including great generals like Napoleon, great scientists like Einstein, and great inventors like Edison, as well as Seymour Cray. Following the failure of the 8600 project, Seymour needed to start over on a new computer design. But Control Data was either unwilling or unable to provide the funding he needed, so Seymour left Control Data and formed a new company, Cray Research, in 1972. And it was then that he began designing the Cray-1. Now, both Los Alamos and Livermore had planned to acquire the 8600, but because it wasn't successful, these two labs investigated the possibility of using the first generation of vector supercomputers to fill their needs, the TI-ASC and the Star 100. Both of the computers in this first vector generation were memory-to-memory vector designs that were developed in the late 60s and early 1970s. Both were a little late, with deliveries occurring mostly around 1974 and 75. And both Los Alamos and Livermore, as well as General Motors, selected the Star 100 as their next major scientific computer. However, when the final specifications of the Star 100 were announced in 1974, we became very concerned because the scalar performance was far less than expected. Some users claimed that it was not only slower than a 7600 in scalar mode, but slower than a 6600. And the startup time for memory-to-memory vector operations was so long, the machine was effective only on long vectors. When we learned of these and other problems, those of us in the computing division at Los Alamos immediately called a meeting with our major users in the weapons division and described the strengths and weaknesses of the Star 100. When we asked them whether they thought they could make effective use of such a machine, their unanimous answer was an emphatic no. The two divisions then agreed on a policy. It is better to get no machine than to get the wrong machine. That is, we were willing to completely cancel the order with CDC rather than to accept a Star 100. This decision caused some legal problems because we had a contract for a Star 100. But after vigorous discussions with CDC, it was agreed that Los Alamos would honor the full contractual payment if CDC would deliver two 7600s and some smaller computers rather than a Star 100, which is what they did. And the Star 100, intended for Los Alamos, was then acquired by Livermore as a second vector machine. Now, one of the questions the organizers of this conference have put to the speakers is, why did the Cray-1 succeed as well as it did? Now, there's several ways to answer that question, of course, and one is to re-examine the relationship of the Cray-1 to that first generation of vector supercomputers. Now, because the ASC and the Star 100 were the pioneers in the design of vector supercomputers, they revealed some important problems, as we just noted. Seymour had the advantage of learning from the first generation of vector computer designs, observing the problems they encountered, and therefore being able to design around them. Referring to the Star 100, he said, "The pioneer never wins. It's always easier to be the one who goes second." Seymour succeeded with the Cray-1 in part because he walked in the footprints of the vector pioneers. But knowing a problem exists is not the same thing as knowing how to solve it. And when Seymour designed his vector computer with fast scalar performance and fast-access vector registers, these were acts of genuine creativity. Nevertheless, we need to give credit to those who developed the first generation of vector supercomputers for having the ingenuity and the daring to explore new designs, as well as to Seymour Cray for his design that solved many of these early problems. Now, Seymour's rule about the hazards of pioneering brings up the consideration of other design guidelines that he used that contributed to his notable successes. One is, start with a blank sheet of paper. Seymour evidently agreed with Herman Melville, who said, "It is better to fail in originality than to succeed in imitation." However, no inventor starts with a completely blank sheet of paper, but begins with the knowledge, the tools, and techniques that are already known from earlier successes and failures, and then contributes something new and creative, as shown in this diagram. You'll notice that I've condensed the history of technology to a logic diagram with only two AND gates and a feedback loop. So in spite of his rule for starting with a blank sheet of paper, Seymour's designs were always a mixture of continuity and discontinuity. In an interview at the Smithsonian, he remarked, "Every machine I have designed has been a clear descendant of another in its structure." Now this figure shows some of the dependencies of the Cray-1 on earlier designs. This is a cladogram, a kind of diagram that's commonly used in biology to show the relationships of species that have common ancestors. And it does that very nicely for computers as well. I would like to see one of these things drawn up by Burton Smith, who knows more about computer architecture than I do. Seymour's statement about his new machines being descendants of earlier ones emphasizes continuity, but discontinuity also characterized some of his designs. For example, his first design, the control circuits for the Univac 1103 in the early 1950s, was a machine with 36-bit words, fixed point arithmetic, cathode ray tube storage, and vacuum tube logic. Yet the first machine he designed for control data, the 1604, was radically different. 48-bit words, both fixed and floating point arithmetic, core storage, and transistor logic. Perhaps Seymour's rule about starting with a blank sheet of paper can best be interpreted to mean that, all other things being equal, compatibility is a desirable attribute in a computer, but he was willing to forego compatibility in order to achieve high performance. He did that in many of his designs, including the Cray-1. A second design guideline that Seymour used was to keep the design simple. Simple instruction sets are a Seymour Cray legacy. His first instruction set for the 1103 had 41 instructions. His next one, the 1604, had 62. The 6600 had 64. The 7600 had 82, and the Cray-1 had 128. Now compare that to the history of instruction sets for some machines in IBM's early history. The 701, first delivered in 1953, had just 32 instructions. There is an original RISC, really a reduced instruction set computer. The IBM 704 had 86, the 7090 had 180, the 7094 had 274, and the IBM Stretch had, how many would you guess? 750. IBM learned their lesson with a bloated instruction set for the Stretch, and their later computer designs had far fewer instructions. John Koch, a member of the Stretch design team, is sometimes credited with the invention of the idea for a reduced instruction set computer, but others credit Seymour Cray's 6600 as being RISC-like and use the acronym, as I've shown here, really invented by Seymour Cray. A third design guideline that Seymour used was that the design team should be small and led by a single decision maker. When the 6600 was announced in 1963, Thomas J. Watson of IBM was disturbed to learn that it was the performance leader among scientific computers, and that it had been developed by Seymour Cray with a team of just 34 members, including the janitor. Whereas the Stretch design team included over 300 members. He wanted to know how it was possible for Seymour to succeed with so few people. Now, when Seymour heard that question, he responded that Mr. Watson had provided his own answer. It was having a small design team that led to his success. I once asked Seymour how many people worked on the design of the Cray-1 and how much it cost. He said 35 people and $5 million. And soon after that, I was in a meeting with Gene Amdahl, and I asked him the same questions about his first computer for the Amdahl Corporation. The answer was interesting. It scaled by a factor of 10, 350 people and $50 million. And that gives us some indication of the value that Seymour Cray personally brought to computer design and development process. But keeping a design team small is easier said than done. Seymour's design teams could be small only because Seymour himself did so many things usually done by many people. Gordon Bell calls Seymour a tall, thin man, meaning that Seymour knew and worked on many things in the design process, from the circuits to the architecture to the software to the plumbing. A fourth guideline that Seymour used was to work in silence and isolation. Seymour was noted for his unorthodox working style. He preferred working alone in the evenings and late into the night when no one else was around, then coming to work the next day just in time for a working lunch at the Flame Restaurant in Chippewa Falls. There's also the story of how he dug a tunnel under his house in order to be alone, and when he got stuck on a problem at work, he would go dig in his tunnel. He claimed that elves were at work in his office in his absence, and when he returned from a dig, they had often already solved his problems. We might summarize Seymour's rule about working in silence and alone by paraphrasing Longfellow. Heights by Seymour reached and kept were not attained by sudden flight, but he, while his companions slept, was toiling upward in the night. Literally true. One final thought. I seem to be late on those. We'll never know what things Seymour would have attempted and achieved had he lived longer, but we can be sure that they would have been ingenious, daring, and creative. It was always a joy to stand by in awe and watch such a brilliant mind at work. He is sorely missed. Thank you very much for your invitation to speak to you.
Well, as soon as the tear goes away here, we'll try to talk. Can you hear me through this microphone as well? No? Then why am I carrying it around? But we'll try this one. I'm Bo Ewald, and many of you I've known for, I see so many familiar faces out there. I've known folks for 30 or more years, some of you, and my given name is Robert. In sort of concert with what we're talking about tonight, I thought I'd take you through another little mathematical thing here that's going on. My given name is Robert, and of course, as an American kid, you get nicknames. Robert has 6 letters, so pretty quickly you become Bobby. And I think, in fact, probably Forrest has called me that a few times. And then sometime along in high school, my friends, I guess as I got bigger, called me Big E, since my last name's Ewald, and that had 4 letters, so I went 654. And then after a while, you get called Bob, which had 3 letters. And then when I arrived at Los Alamos, they were making the name tag for my office. And these were these little Bakelite, or I don't know what they were, probably predecessors of plastic. And the person making it had started to type on, or scrawl, or whatever they did, scribe, Bob Ewald, but they started right in the middle. They didn't backspace for it. And so they did 2 letters and then quit. So on one side it said Bo, and then they turned it over, and on the other side it said Bob Ewald. And so that showed up on the door of my office at the lab. And I made the mistake of telling a fellow named Alex Marisak, whom some of you would know, and another fellow named Andy White about this funny thing that had happened. Well, every day then when I came to work, the name tag was always turned the other way. So that was how I lost yet another letter. And on average here, I've lost a letter every 12 to 15 years. And so I think I'm headed for B and then off the air. I think it's predictable how long this is going to go. And does this work yet, or is this one really just for the... It says it's on and all kinds of stuff. I'm going to have a hard time standing here, so, but we'll try. I went to Los Alamos actually at the end of 1976 to work on that first Cray. I was did a lot of early work in computer graphics, and in fact was drawn to Los Alamos because of what it was doing in computer graphics, and also because the Cray was there. And my first job was to put up a high-performance graphics system on the Cray. And is this working yet? And in doing that, then we interfaced our graphics system with the Cray, so really was sort of a systems programmer, application programmer, and then ended up working in the operating systems group that Forrest and John Morrison had formed, and then ended up running computing at Los Alamos and did that for 4 or 5 years, and then went to Cray for the next 10 or 12, and then was at Silicon Graphics. In fact, this was one of the buildings in our domain at Silicon Graphics when I was there. And now actually have come back into high-performance computing. We have a little company called Linux Networks, and we were pleased to sponsor this with Pete Ungaro from Cray, sponsor the event tonight. So we're doing high-performance computing, not using the same business model that we have in others, but using off-the-shelf components and Linux operating system, and trying to basically do, again, what Cray did during the 80s. And so stay tuned, and we'll hope we can do that. I'm going to talk a little bit about what the software environment was like
in those days, and so we've called this From the Wilderness to the Wars. And the wars here were not Star Wars. They really were far more serious than that. They were operating system wars, which were religious. Many of you were involved in them. They went on for many years. And in fact, we're in World War III of those right now related to Linux. So as we go along, we'll recall what happened to the best of our ability. If I get it grossly wrong, please help, but this is what I remember. And as I was thinking about this and talking with Jack and Bill and Burton about what we're going to talk about, I was reminded of our times at Los Alamos when there was one of our really renowned elder... that's okay. That's okay. One of our renowned elderly scientists, who was far older than probably the three of us put together at the time, had just gotten married. And his new wife was quite a bit younger than he was, and was concerned, you know, that if they... I'll try to tell this in not too off-color a way, but was concerned that he might, you know, if they slept together all the time, might expire. And so the agreement that they had was that after they got married, in fact, they would have 2 separate bedrooms. And he agreed to that. He thought that was just fine. And this, by the way, is not Bob Thorne from Los Alamos days. So he agreed to that, and on the day they got married, that night, they each went to their separate rooms, and she got the expected knock on the door, and the fellow came in, and they consummated their marriage and just had a wonderful time, I suppose. And then she thought, oh, gee, that's surprising and great, and went to sleep, and about 2 hours later, there was another knock on the door, and the fellow came back in, and the same thing, and she was astounded. He left, and about 2 hours later, another knock on the door. And she said, I am completely astounded. What, you know, wow, just unbelievable that this is happening. And he said, have I been here before? And so we're doing our best to remember things, and we'll remember some of those well, and others, it could be okay as well. So with that, we'll talk just a little bit about sort of from the wilderness to the wars. When Seymour did this first machine, in fact, there were probably 35 people in the company, but there were also another 60 or 70 of what Seymour called Chippewa ladies, the ladies. It was the ladies who actually did the wiring. And do folks remember about how many miles of wire were in this thing? There are various estimates of 5 to 6 and then 60 to 70. And I think it's more in the range of the 60 number. And it was those ladies who did that. And over a period of time, they started having these very fancy and stylish Chippewa smocks, which also helped prevent electrostatic discharge. So this was early Cray wear, though you were hard-pressed to ever see Seymour wear one. But Les Davis, who we'll talk a little bit about later, always had one on, or nearly always had one on. And the Cray-1, when I first got to Los Alamos, was about 6 feet tall. And it was, you could tell it was in its infancy, because later on it was about 6'3" or 6'4", so it was growing as it was there. And of course that was as SecDed memory was added to it when it came back, so it got taller over a period of time. And just a couple of comments about the cushions that were on it. Burton, we in fact did have one machine which did not have the cushions on it, and it was the first machine because in about 1978, the fire inspector and the insurance man came through our central computing facility. And they're checking everything for underwriters' laboratory stamps and this and that. And of course, here you have a computer that's consuming a few kilowatts. And on top of the power supplies is plywood from the equivalent of Builder's Square or Home Depot in between Chippewa and Eau Claire. And on top of it was this sort of Naugahyde type stuff with flammable foam in between. And so you could imagine what the fire inspector said about that. This has to go, and we said, no, but it's part of the aesthetic part of this. No, it has to go. So in fact, we had to take the cushions off of that machine. We did try to get Cray to replace those. It was clear that even Les Davis had no desire to do that. So for a few months, that machine looked like that, until one day Norm Morse, who was with us at Los Alamos, found some fire-resistant Underwriter laboratory-approved plywood and took it down to Al's Upholstery in Espanola, New Mexico, and they reupholstered those cushions, and after that it actually had the cushions back on it. And as far as the colors of those Crays were concerned, in the case of Los Alamos, during my tenure there, by the time I left, we had 5 Crays. And of the 4 that we purchased sort of under my watch, I turned over the color selection to Levon Haar, who was my assistant. And as you'll see from my current clothing and other, in fact, I have zero taste and not much knowledge of color, style, or anything else. And so she was actually the one who picked the colors of the Los Alamos machines, being far better than I. And a little later on, when I was at Cray and we were introducing, maybe it actually was the T3D, the first of the highly parallel systems from us. And we were doing it back in the East someplace. And so we had gone through this introduction of the machine, and a fellow probably from the Pittsburgh Supercomputing Center yelled out from the audience of, okay, what colors does it come in? And it was the standard Cray response, if you're going to spend $10 million, we'll paint it whatever color you want. And so that was sort of what we always tried to do. In 1976 and 77 at Los Alamos, these were the major computers that were there. There was the first Cray-1, and the operating system was a question mark because there was no operating system. We had 4 7600s, and we were just finishing migrating from the Chili Ridge operating system, or CROSS, a Los Alamos grown batch operating system, to the Livermore time-sharing system on the 7600s. We still ran CROSS on some of the 7600s at night for batch reasons, or compatibility reasons. And then we had some 6600s still, and a Cyber 73, and an IBM photo store, and the museum has elements of one of those. That's a whole nother topic for another session sometime. But if you haven't seen one of those things, those were the most unbelievable combination of chemical, electrical, mechanical, and optical, and magnetic machines that you ever saw. And if you put those, basically what they did was on a little piece of film was expose a bit, make a dot, a bit, and would fill up this little chip with bits, and then the machine automatically would run that through a film processor that it had, and then store it in a little box and then be able to retrieve those. And you could tell in the morning when you came into the central computing facility, you could tell if it had been a heavy night of storing data or not because of the smell. It smelled like you were at Kodak or something like that. And you know that the chemical, electromechanical, mechanical, optical, if you put all of those together, the initials are chemo. And I think I wonder why more people have survived being around those things, because they really did give you quite a dose of things, quite a dose of scent in the morning. And then Los Alamos was also bringing up the common file system, which was really the predecessor of a lot of the big network storage systems, the way network storage has evolved. And I don't expect anybody to read this, but I extracted this from one of our papers in 1977 about what was then the LASL, the Los Alamos Scientific Laboratory, Integrated Computing Network. And the boxes that are at the top in the middle are what we call the worker computers. And those were connected to, as we were moving to time sharing, connected out through the boxes on the right, which say KCC for Keyboard Concentrator Computer. And so users would have eventually desktops, workstations, terminals in their offices, and be able to come through that set of machines into another set of PDP-11s, and then finally through the cell, those bigger blocks, our system engineering laboratory they were from Florida, really was the first 32-bit mini computer. Huge, really high-speed bus, and they were tremendous for file transfers in 1976 and 1977. And then in the back end of the network, we had the storage systems. And you know what this network did and what was going on at Livermore were really precursors for what you saw over the next 20 years evolving in networks throughout the world. What we did and what our friends at Livermore and Sandia folks were doing the same were basically taking what were the individual functions of a computer and spreading those out into the network. Today we would call those compute servers. We ended up having, in our case, we had network storage control or network security controllers. We had storage, centralized storage systems. So it really was a tremendous place to work and really was right at the state of the art. And the challenge was to get the Cray to fit into that network. And the way that you got at the Cray in 1976 was you had, in some cases, an electrostatic printer that ran at the blazing speed of 110 bits per second, and then, which is 10 characters per second. And over a period of time, we got all the way up to 9,600 bits per second, and then faster over time. And we had these KCC things. They were PDP-11s, and they each, over a period of time, would end up serving 100 to a couple of hundred terminals that were connected to them. And then those were connected to yet another layer of PDP-11s that we called syncs or synchronizers. And then those messages went, I couldn't find a picture of a cell machine anywhere, but then the high-speed backbone that we had was based on these cell 3255s maybe, and then from there into the worker computers. And of course, at that time, the big worker computers we had were the 7600s to which the Cray was added. And on the 7600s by then, we had LTSS running most of the time. And LTSS was written in everybody's favorite operating system implementation language called LRL-Tran. And what kind of a language was that? Fortran with pointers, effectively. And so you know, folks, Fortran was Fortran, and then Fortran with pointers was LRL-Tran. And another interesting thing, the 6600s and 7600s had 60-bit words, and they used display code to represent the characters. And that was a little unique, 60 bits, display code. You could represent 64 characters, 63 or 64 characters, no lowercase. And but you could pack 10 of those characters per word. And as the Cray came along, in fact, it had no software. We ran, no is a little too strong. Of the 35 people who designed the Cray, there were 3 more added, and those were the software people in 76 and early 77. And there was a compiler person, an operating system person, and an I/O person. And Dick Nelson, whom some of you would know, was really one of the premier compiler people in the history of this business. And then if I remember right, Paul Johnson was the operating system person at Cray, and Bob Allen, I think, was the I/O person. That sound right, George? Yeah. And they had created a thing called the benchmark operating system, or affectionately known as BOSS. And that's what ran on the Cray, and it was really just sort of a monitor. You could ship an executable file or a file that needed to be loaded over. You could ship data over, and then BOSS had enough smarts to actually load it and run it, and then game was over. And so from the 7600, you would then have to retrieve the output, retrieve any more data you wanted, and that sort of thing. So it was the ultimate in batch operating systems, and in that you could run one job at a time, period, and it really ran under the control of the 7600. So the we ended up consuming a heck of a lot of 7600 resources in running those systems. And then a few other little complications of the 64-bit words, ASCII versus display code, and on and on and on. And that environment involved using the FTN compiler, and I'll just tell one little story and then speed along here. The FTN compiler was actually a control data compiler. In those days, we got source license to everything. And there was a fellow named Steve Hugh who ran the compiler group at Los Alamos and took that FTN compiler and fixed it so that it would generate Cray assembly language. And then we had vector primitives, and so the user would code in sort of vector primitives, run it through this cross compiler, and then would link it with basically vector libraries, if you will, create a Cray executable, would get shipped over with the data and run on the Cray side. And, you know, you can imagine 60 bits, 64, display code, ASCII, and on and on and on. So that really was the environment then. And in 1977, the laboratory and the DOE community really were talking about there was huge debates about what operating systems. Should you run time sharing on these big machines? No, they were too valuable to spend on things like that. So from Washington, there really was a strong push to run batch operating systems on this. Forrest Baskett, who's in the audience, Forrest, raise your hand. So led the design of Demos, which was early, great message passing based operating system, really ahead of its time, operated in the batch environment, but really was set up to operate in a parallel distributed manner. And so in fact, in 77 and 78, we were bringing that up. Of course, it had its own implementation language called Model, which Jim Morris wrote for us, and its own set of t-shirts. So we had the Demos t-shirts, and then at that point, you could actually then start running on the Cray in a native mode, and that was a huge step forward for us. And as we went along, then there were other systems that were run on these Crays, but that was the status then. And this, in fact, is a not very good picture, but of the first real graphics application that ran on these machines. This is an Evans and Sutherland Picture System 2 that we got running with Demos, and this is an unclassified weapons. This is Alex Marisak, for those of you who are Los Alamos alums, to look at. So, you know, that was sort of how a snapshot, at least, of what it was like with the Cray to be able to use it. And then in the operating system world, Cray, when NCAR bought their first Cray, part of the contract was that Cray should develop an operating system. So Margaret Loftus was hired by Cray at that point and developed the Cray operating system called COS. And when the Cray started going here to Livermore, particularly to the MFE Center, Hans Breinus and Dieter Fuss and gang ported LTSS over to those systems. And then later on, Cray started moving down the Unix path and was developing its, after lots of other wars, was developing its own version of, actually was developing 3 different versions of Unix, and ended up settling on one of those. And so that was called, I'll try to not embarrass myself or anyone else here. That was Unicos. And in fact, we had shirts like this, and they're talking about, I think the one on the back says, riding the MTTI wave. Maybe just one little word about that. When that first Cray-1 came, the lab did a report on its performance and all the rest. And in that, during the 6-month period, mean time to interruption was measured in 20-day intervals. And during that 6-month period, the mean time to interruption of that Cray ranged from a low of 2.5 hours to a high of about 6.5 hours. And Tom Keller, who wrote the report, said no trends were able to be observed. 90% roughly of the downtime of that machine was caused by parity errors. And so the laboratory, of course, said we need sec dead memory or something of the sort to fix that, Seymour. And that was when Seymour made his famous comment, parity is for farmers. However, at one of his sort of Christmas retreats that he always took and came back with lots of new ideas. In fact, then the machine started coming back with SecDed, and in fact, that was how ours got even taller. So just a few things. This is sort of the computer scientist equivalent of the time question of, instead of how many angels can you fit on the head of a pin, it's how many computing wizards can you fit on a Cray-1. And just would point out a couple of folks, heard of Hamming code? Dick Hamming, upper left. Folks from Livermore would recognize Sid Fernbach sitting on the far left. Bert Herzog, University of Michigan. Jim Brown, University of Texas, standing in the back, who was also with Forrest, a contributor to the design of Demos. And then Al Arisman, standing far right from Boeing. And we had lots of folks who were interested in the Cray. This fellow in the middle is Bill Spack, who actually was the procurement wizard and figured out how to buy all these different computers. And the fellow looking at that is Paul Robinson, who ended up being the president of Sandia and the director of Sandia Labs. Anybody recognize this fellow? The one in the middle there. Tom Brokaw, yeah, exactly. About 20 years ago on the event of the lab's, must have been 40th anniversary, 40th birthday. Anybody recognize the fellow on the far left? With mustache. Stand out here, Burton, you'll see who it is. And then we also were very interested in what was going on in Japan, and so we took a trip with our friends from Livermore. So George, Michael, and Harry Reynolds, John Ranaletti, and then the three amigos here. And we started learning about the Japanese supercomputers, and never actually bought one, but we learned about them. And anytime that I think you talk about Cray Research, should also talk about Les Davis, because Les was Seymour's right-hand person for 30 years. And Les still lives in Chippewa. We had tried to get him to come tonight, but he has other things going on, and really should also say thanks to Les for all that he has done for this. And so with that, we'll leave it at that, and would next turn it over to Bill Buzbee.
Can you hear me now? I'm happy to be the speaker you've all been waiting for, the last one. And I'll repeat the caveat that some of my predecessors have made note of, and as many of you know, unlike wine, memory does not improve with age, and so we're working from memory tonight, okay? I'd like to fairly quickly cover these topics. My favorite Seymour story, I think everybody who knew Seymour had at least one favorite story about him. And then a few more words about computers and computing in the 70s, and particularly the merits of the Cray-1 for that era. And while it is the case that Los Alamos got serial 1 of the Cray-1, those of us who have been affiliated with NCAR take a certain smug satisfaction in the fact that the first production model of the Cray-1 went to NCAR, and I'll explain that shortly. It's also the case that the only Cray-3 installed outside of the company was installed at NCAR, all of which reminds me of Grace Hopper's definition of nanosecond, and we'll conclude with that. I first met Seymour back in the mid-70s at Los Alamos and through the 7600 and what have you. I mean the Cray-1. And in the early 80s, I attended a Cray Research customer event in Minneapolis, and Seymour happened to be the after-dinner speaker. And on that occasion, he began his talk with a short synopsis of his career. He said that he began his career in the 50s as an electrical engineer, and as such, he was able to support the family. And then in the 60s, when he employed three-dimensional packaging in the 6600, he had become a mechanical engineer, and he was able to open a savings account. Life got better. And then in the mid-70s, as he employed liquid cooling in the Cray-1, he said he became a plumber. And as often the case with plumbers, he became financially comfortable. Of course, comforts that were well earned and deserved. A few words about computing in the 70s. You saw this graphic earlier, one of Jack Worlton's creations, and the key point here is that the growth rate in execution bandwidth was diminishing with time. And that was a worrisome point to us in the 70s in the HPC arena. And of course, one way to circumvent that trend was to incorporate parallelism into the system. And as other speakers have noted, By the mid-'70s, there was a surprising amount of parallelism in the systems. Instruction stack, multiple registers, multiple functional units, pipelined functional units, segmented memories, what have you. And to some extent, the Cray-1 simply extended these capabilities, encompassing vector mode, but also offering some new and innovative capabilities as well. The key, in my mind, in my memory, aspect of the Cray-1 were the vector registers. And they had this ingenious characteristic that you could transfer data to or from memory into a vector register simply by specifying the first address of the first element, the memory spacing between consecutive elements, and the total number of words in the to be loaded. And I'll talk more about that in just a moment, but that fit our needs very nicely. As others have noted, you could chain 2 or more vector operations together, producing 2 or more arithmetic operations per cycle. And then there was the scatter-gather, an instruction by which you could load into a vector register the contents of memories, addresses stored in a list, or vice versa, store a vector register into the memory locations given in a list. Now, back in the 70s, at least as my memory recalls, most scientific models only encompassed 2 space dimensions. They were, of course, a series of nested do loops, and the inner loop typically swept across grid points either in a row or a column. And typically, a row or a column had at most a few dozen grid points in it. So as Jack pointed out earlier, this matter of short vectors was very important. And this problem of trying to find long vectors was a tough one, we'll put it that way. At any rate, given the characteristics of the Cray that I just described, that vector register and the ability to load, store, and what have you, it was straightforward to vectorize existing programs. In fact, with a little thought on the part of the user, the compiler could do a pretty good job of vectorizing code. And that was a remarkable payoff, and that combined with good performance on short vectors, in my mind, is what led the Cray-1 to become very rapidly become a market leader. Now, how is it that NCAR got the first, quote, production model of the Cray-1? Bob briefly alluded to this. Serial 1 of the Cray-1 did not have parity checking in memory. And as you heard from Jack, part of the deal between Los Alamos and Cray was that Los Alamos would evaluate, test, and what have you, Serial 1, which it did. And in the course of doing that, it became evident, and Seymour eventually acknowledged that parity checking would be a good thing to have. At that point in time, he was already underway with the assembly of the Serial 2, which he then aborted and proceeded to build Serial 3, incorporating parity checking into the memory. Now, at the same time, NCAR, or during that period of time, NCAR had made the decision to acquire Cray-1, and further had financed it through a bond issue with the county of Boulder. And so NCAR was in a position to put the money on the table, payment in full. And being a new startup company, clearly that wasn't a lucrative opportunity to Cray Research. And so Serial 3 went to NCAR, and then Serial 4 went to Los Alamos to replace Serial 1. So again, we at NCAR take a certain amount of smug satisfaction in this. It's also the case, again, that the Cray-3 NCAR was the only site that it was installed at. As many as you know, Seymour relocated to Colorado Springs in the late 80s to establish Cray Computer Corp and to develop the Cray-3. Coincidentally, I relocated to NCAR at about that same time from Los Alamos. Initially, Livermore had an option to acquire Serial 1 of the Cray-3, but as the project fell behind in schedule, like 1991, I believe it was, Livermore had to do something else, and so they relinquished that option. And that created a certain amount of turmoil for Cray Computer. And shortly thereafter, Gary Jensen, who headed our operations group within the NCAR computing division, stopped by one morning to chat about this. And in the course of our conversation, Gary suggested, gee, why don't some of us drive down to Colorado Springs and ask Seymour what NCAR might do to help. And in fact, top management joined us and made the trip down there. And we posed that question to Seymour, and in about a millisecond, he responded, how about showcasing the Cray-3? And we did, and it was a good deal for both of us. Here is a photograph of the Cray-3 as it's on the floor at NCAR. The entire computer, well, at least the memory and the CPU and what have you, is this? Okay, well, the plexiglass canopy there, the entire memory processors and what have you are underneath that canopy. So it was 4 processors running at a 2 nanosecond clock. The technology was gallium arsenide. And as you can see, this was literally the world's first desktop supercomputer. Now, it is the case, I mean, literally, you could put this thing on the top of your desk. There is the problem of what do you do with the power and cooling system. So probably better just to use it as a desk-side supercomputer. But at any rate, anytime I look at this photo, I am reminded of Grace Hopper's definition of nanosecond. As many of you may recall, she used to hold up a piece of wire about 11 3/4 inches long and say, ladies and gentlemen, this is a nanosecond. Because, in fact, a photon of light travels about 11 3/4 inches in a nanosecond. Electrons typically travel a little slower depending on the medium they're in. So it was a wonderful way to make the point that short wires are good. And in fact, in the 80s and 90s, many of us in the HPC arena, anytime a new supercomputer was announced, the first thing we'd do is check the footprint. And if it had a big footprint, chances were there were some long wires in there somewhere, and you really wanted to be careful of it. Obviously, as you look at this photo here, we were quite happy with the Cray-3. We weren't worried at all with it. A wonderful design by an ingenious engineer, and thanks very much to the organizers for the opportunity to join in this celebration and to help honor Seymour. My thanks also to the Arctic Region Supercomputing Center, who are helping with my travel support this evening. This is a photograph of Denali, the tallest mountain in North America, in Alaska, situated about 100 miles from Fairbanks, the home of the Arctic Region Supercomputing. Thanks again, and Burton, you're up.
Thank you all very much. Now it's the audience's turn. I don't know how much time we can scrape together here at the end of the session, but please, some of you know a lot about this topic, and I think we want to hear from you if we can. If you have some comment to make or some question to ask, please come to one of the 2 microphones situated at the head of the aisles here. And please don't be shy. Need a little audio.
Hello? Am I on? Thank you. My name's Sean Murphy. I've been in the Valley for about 10 years. When I first came out of school in 1993 as a mechanical engineer, I went to Colorado Springs and started knocking on doors, and Cray Computer was one of the first doors I knocked on. Unfortunately, they were just on the way out and kind of missed the peak of it, but I met some other fellows who were working with Cray and were sort of on the side starting another little incarnation of Cray when he was killed in a car accident in Colorado Springs. So that was kind of a tragedy. I was like 6 years old when the Cray-1 came out, but you guys are kind of all reminiscing about it, but it didn't really capture like what was, what could this do? How much faster was it than everything else? And what did you use it for? And what was the real sort of thing about it?
To net it out, it was about twice as fast as the CDC 7600s were in scalar mode.
So you wouldn't even have to do any of this fancy schmancy vector stuff. You were still twice as fast as the world's fastest machine last week.
It ran at about 12 and a half nanoseconds, and the 7600s must have been
27? Yeah.
And in vector mode, it averaging about 4 times for the set of kernels that we usually use, about 4 times the speed of the 7600. So depending on the balance of scalar and vector you had, it was from 2 to approaching 4 in some cases. And for some codes, it was like 10 times or more faster than the 7600. And Los Alamos' primary mission in those days was, in fact, nuclear weapons design. So it was used for classified weapons design.
Yeah, mostly solving differential equations. Not all, but largely that.
Comment, Bert?
Yeah, Jack?
Yeah. When we got our Cray-1, our users discovered that scalar mode was so fast that they could take a 7600 code, plunk it on a Cray-1 with very little work, and it ran twice as fast. And so a lot of those people just ran their 7600 codes on a Cray-1 without doing hardly anything at all. No vectorization. They used it as a scalar box and got a factor of 2 out of it. And it took an order from Bob Thorne, the head of the division leader, to force them to vectorize it. So in a sense, its scalar box was so fast it was its downfall for a while.
There is the original report from December of 1976 is the original Cray-1 evaluation report by Tom Keller. And I think if the original performance report on the Cray-1 to see if in fact it would meet the performance requirements that it needed to meet to be a Class 6 computer and therefore be able to be acquired were evaluated here by Tom Keller. And so it's quite interesting. It's old stuff, but it's quite interesting to read. And in fact, in here they point out that the mean time to interruption ranged from this 2.5 to 6.5 hours with no pattern. And in it, Tom and team speculated that in fact, if the machine had Sept dead, that MTTI would probably be 9 times better than that, and that would take it up to it would only fail once a day. And in today's world, that's crazy, but that really was quite an advance for the amount of computing you could get done in that day.
One of the technology slides mentioned the machine was built out of Mechl 3 from Motorola. However, the Cray red herring, when they went public, mentioned that Fairchild was the largest stockholder. The reason being that they had supplied the Fairchild F100K for the prototype, accepting stock rather than cash. So when did they change and why did they change? What was the problem with the Fairchild stuff that they switched to Motorola?
Yeah, I don't know the answer to that. I know that both Fairchild and Cray were able to supply parts for these things, but I don't really know why or what happened there. I could conjecture one thing, of course, and that is that the 100K Eckel had faster edge speeds in spite of the fact that its gate delays were about the same. And that might have tipped the balance. Anybody else have anything for us? Yeah. Yeah, there was that too. Motorola always had a hard time figuring out how to make memory chips. I mean, throughout their whole time. And Fairchild made memory chips a lot for Cray. That's a good point. Yeah.
Please support me for a moment. I'm a little shy about this, but I actually got to talk to Seymour. I worked for him in 1982. We were doing the 10th anniversary symposium for his machines, and he said to me, Diane, when I worked for CDC, I was walking down the hall one day, and some guy told me, you can do all the Laplace transforms you want in the world, but it's the length of wire that's going to make the big difference. That's what you got to do. And he said, I got a lot less respect, but a lot more money once he recognized that. And then he went on and he said, you know, and then when I realized how I had to vectorize everything, I got into cabinet making. And I got a lot more money and a lot more less respect. And he said, so when it came along to the Cray, we were working on the Cray-1 at the time, selling it, but he was working on the Cray-2, of course. He said, now I'm a plumber. I'm getting a lot less money and a lot more respect. He said, but the point is, I am selling these machines, and I can make them work faster. And I had come from Carnegie Mellon where, I mean, I was really some idiot kid who thought VLSI was everything. And here's this guy telling me that you can run things as fast as you want, but you're going to burn stuff up. Get this stuff done fast and in duplicity, in multiplicity, and that's what's going to work. And I carried it with me forever. It helped me make a career. The guy gave me just a 10-minute sermon on his life, and it was like, wow, what this guy could do. So I just want to share with y'all that he had the moments where he'd step down and just sit with someone and talk to them about what he was doing and why it made sense to him. And that was an absolutely fantastic part of the guy that I couldn't tell. I don't know the rest of you, but for me it was immeasurable what it meant to me.
Burton, could I tag onto that with one little story? I have lots of anecdotes like that I won't share, but one that sort of changed what I was doing. I had been at Los Alamos for 8 or 9 years and been running the computing division the last 4 or 5 years that I was there. It was great and wonderful, and really it was outstanding. But I had never spent any real time in private industry, and of the companies that I knew, Cray was the one that I had the most respect for. So, and I'd gotten to know Seymour fairly well. So I decided really it was time for me to do something else, and so I called Seymour up one day. I really screwed up my courage to do this, to call Seymour. So I called Seymour and said, Seymour, I've been here for quite a while, and I'm thinking about doing something different. And he said, he was quiet, and he said, oh, okay. And I said, I have never spent any time in private industry and would like to try that, and I've never been in sales and marketing and would kind of like to try to learn what that's about. And so without any pressure, if there's something that you think I could do at Cray, would sure love to hear about it. And then the phone went dead, and I thought, did I lose the connection or what happened? And then those of you who know him, he had a characteristic little chuckle, and I could just see his eyes twinkling. And he said, Bo, that's one of the dumbest things I've ever heard. Do you know how hard it is to sell $10 million computers? We'd all be a lot better off if you just stayed at Los Alamos and kept buying them. And so, of course, I thought with a challenge like that, I must go to Cray and see if we could do anything about it.
Yes, sir.
All right. Robert Garner, and I was a young kid in college when Cray was busy doing his stuff, so he was an inspiration to all of us who had no idea how he managed to twist the laws of physics. Later in my design career, I saw many people who went up against the laws and failed. I probably have about 100 questions, like what kind of design tools did he use? I remember one of the jokes was when Apple bought a Cray, he would say, well, I used the Apple to design the Cray.
He did.
Yes, and or his, just his head. But anyways, I've been telling some stories, and I wanted to maybe hear if I've been telling accurate stories. I actually designed a gallium arsenide machine at Sun, and we put that on the shelf in the same way, in some sense, that perhaps Seymour had difficulty with gallium arsenide. There were two things I've been saying. One, which is he was forced to move from Chippewa Falls to Colorado Springs to get the manufacturing capability to build his extremely fine-pitched multi-chip modules. That's my first question, whether that was true. I've also been suggesting Cray spent about $200 million in R&D on the Cray-3. I guess that's my second question. My third question is, when did he have a revelation? Many of us, loved Meckel and differential lines and balanced signals and all the joys of that logic family, but were blinded to the increases in CMOS capability, even at the single CPU level. Was there a moment when Seymour saw the light and saw CMOS coming up as your tailpipe? That's my third question. Thank you.
Well, if we can remember the questions. Back to our earlier comment.
The first one was, did he in fact move from Chippewa to Colorado Springs for the MCM technology manufacturing?
Yeah, I'll give you my perspective on that and what I was in the company at the time that happened. And basically Seymour said that I think were two reasons. He said that he had lived in Chippewa most of his adult life, and it was great and a wonderful place to live, but he wanted to live someplace else for a while. And then secondly, he back to one of Jack's points about the way Seymour liked to design things was have a small team, have it isolated, have it be away from other things. And so I think that was the other driving thing. And then thirdly was looking for a facility. So if I remember, this may not be quite accurate, but it's going to be pretty close. Seymour and Jerry, and I think Neil Davenport, who was at Cray at the time and was going to work with Seymour, and Neil's wife, I think that they may have chartered a jet, and they had a list of about 10 places to go visit. And I think it may have been sort of an alphabetic or geographic approach to it. And the first place on the list was Colorado Springs, and they got to Colorado Springs, and Seymour liked it and didn't have to go anyplace else. And so that was really, you know, how extensive that search was. I think it was really, he told me that's how he did it. We had a list, but got to Colorado Springs, and it looked great. There was a great facility. I liked it. It was a nice day. The mountains were there, and that was it. Yeah, and skiing wasn't too far away.
As far as the last question is concerned, I think after the demise of Cray Computer Corporation in Colorado Springs, when Seymour started SRC, I guess at that point he is reported to have said, "I got it," sort of acknowledging that there were some certain advantages to the CMOS world. But let me just say in his defense on this point that the memory bandwidth available on these Seymour Cray machines was largely enabled by the kind of wires and differential signaling and very, very fast stuff that CMOS had a hard time matching for many, many, many years. And that was what endeared his machines to lots of people. And it would have been hard to build even a C90 or a T90 out of CMOS and get that very high bandwidth two-main memory from the processors. So there was another question in there, but I don't remember it.
200 million on the Cray 3?
Oh, yeah, I don't know.
I think that's right.
Bill says yes. So. Eugene.
My memory of the operating system war was much harsher than yours. I was in the latter portion. I think I'm still removing knives and shrapnel from my back. And I could have probably used a real burp gun or a real pistol with a silencer in a few cases. Yeah, well, I think it would have gone much, I think operating systems would have gone much faster. But actually, there's one person, actually, I think, Mike Moose, who Burton also knows, also passed away.
The author of Ping, among other things.
Author of Ping. And
a famous program called BRL-CAD, which he used not only to, assist in visualizing tanks, but even computing their moment of inertia and so on. Very, very creative guy.
Yeah. He died of a similar, didn't his car also roll over?
I think, yes.
Yeah.
So some vehicular accident.
Yeah, and he was supposed to get a Denel core from Burton, and they had to switch over to a Cray 2, I guess. And
no, he did. He
did. Yeah. And he helped out. But
we know about getting a Denel core from Burton.
Yeah. You sure do. That was serial one of that as well. So.
Yeah, that picture was serial one.
So I just wanted to comment that your version of that operating system war was a little historically cleaner than I think it happened.
It was.
Yeah. This is
it was
always the way with
unbelievable.
operating systems. Right. Yeah.
My name's Dave Riddell. I just wanted to throw out, since there are so many wonderful stories and quotes from Seymour, one of my favorites didn't come out tonight, so I just wanted to toss that out. It was right when the whole idea of CMOS running up his tailpipe and building supercomputers out of lots of little chips was just starting to get some momentum behind it. And Seymour, of course, was not very receptive to this idea. And at one point he was heard to say, if you've got a heavy load to pull, which would you rather have, a pair of oxen or 100 chickens?
That's right. That's exactly right. Exactly right. And maybe just a comment on the operating system wars. Yeah, this was the nice, polite version. But at Los Alamos in 1977, 78, 79, 80, 81, 82, or something like that, we had to go to the director's office once a week. There was a meeting in the director's office about how was it coming. There were religious wars over batch systems, demos, CTSS, maybe do what COAS did. It was quite an education, actually.
I'm Jim Kasdorf from the Pittsburgh Supercomputing Center. And
you can have it whatever color you want.
I have to fess up. I was the person who said, what colors does it come in? And then when it was delivered, when it was about to be delivered, they said, you can have gray or black. And we said, Bob Ewald said we can have it any color we wanted.
And what color did you get it?
Black and gold with the Pittsburgh Steelers.
That's right.
And I have to say, I'm absolutely thrilled to be here to see people like Bill and Jack Worlton. I haven't seen you forever, Jack. No, it's great. But I have a story about Bob Ewald and Les Davis. The story was that in Minneapolis, Bob Ewald had a gym. Is this correct? It was called Bo's Gym. And then
he had one at Los Alamos too.
Yeah, and Bob was then transferred to Chippewa Falls. And the story is that people said, "Oh, will there be a Bo's Gym in Chippewa?" And Les Davis said, "In Chippewa, we get our exercise by carrying product to the loading dock."
Which then one day, we put a sign up out there and said, Les's Gym.
Actually, it occurs to me 2 topics you should talk about. Cray Laboratories in Boulder, since very few people have heard of that, and none of you have mentioned Rollwagon.
Cray Laboratories in Boulder, and then John Rollwagon. In fact, John Rollwagon was invited tonight, and for a while it looked like he could come, and I think it would have been wonderful had he been here. He's a far better storyteller, I think, than any of us, and lived those times from inside the company. So, John was, there are lots of stories about John, but one of the favorites about how he and Seymour got together was through the barber. And John was getting his hair cut and saying, I'm thinking of doing something new. He'd been at Controlled Data and, Harvard Business School, MIT, Harvard Business School, and Controlled Data, and then was getting his hair cut. Maybe more, that probably wasn't the first time he got his hair cut since all that happened. And the barber said, well, I think Seymour was here, and I think they're looking for somebody to help them out. So through the barber connection, John got connected with Seymour and ended up then going to Cray. And John was a wonderful complement to Seymour. People characterize Seymour as odd, eccentric, and those sorts of things. And boy, I never felt that with him. He was quiet. He wanted to do what he wanted to do. Didn't like being on stage. And so John was a perfect complement to that because, John was great with the investment community, raised money, worked so well with the customers and all of those sorts of things. So it was a tremendous team to get the company started. I don't know if any of you would like to add to that. And Cray Labs in Boulder, I hadn't thought about that for many years. And so, I'm having one of those lapses. I don't know what to say about it.
I might tell you a little thing about John Rollwagon. After they sold, I don't remember how many machines, not very many, Cray Research went profitable. And so to celebrate the event, he went down to the Cross Pen Company and ordered some pens that were silver on one end and gold on the other. Pen salesman said, "We don't make pens like that." But John was smarter than the average pen salesman, so he said, "Give me some silver ones and gold ones." And he swapped the ends. And then he had the date of profitability engraved on the pen, which was December 28th, 1977. And I brought my old silver and gold pen to leave with the museum here.
Well, I think it's been a very profitable evening, and it's probably time to call a halt to this and go see what shape the cake is in.
Well, thank you all. Thank you, Burton. Thank you, panel. A wonderful evening. Thank you, Jack, for the donations to the Computer Museum. And please join us. Here is the cake. Now, that's the wrong shape. But join us all for cake cutting ceremony.